Okay, Bismillah ar-Rahman ar-Rahim. We will start chapter 5.1, which is the history of the periodic table. The first scientist who arranged the elements was Mendeleev. Mendeleev arranged the elements based on their properties. And as he arranged the elements according to their properties, he found a pattern or certain arrangement of the elements based on their atomic masses. The atomic mass is the average weighted mass for the isotopes of the element, or the average mass of the isotopes of an element. So it means if I have 3 isotopes of hydrogen, hydrogen 1, 1, we have hydrogen 1, 2, and we have hydrogen 1, 3. So when I calculate the atomic mass of these 3 isotopes of hydrogen, I get their average to be the atomic mass generally for an element which is hydrogen. Okay, so this is simply the atomic mass. But we do not use Mendeleev's periodic table nowadays because they found some problems with his table. During his time, some of the elements they didn't or they weren't discovered. During the time after the discovery of these elements, some of them fit with their places and the others they didn't. When he arranged the elements according to their properties, he found that the properties of elements are repeated each row or each period. That's why he named it periodic table. Okay, so he named it periodic table because of the repetition or the pattern or the the repetition or the pattern in the properties. That's why they called it, or he named it, periodic. To correct this problem, another scientist, his name was Moseley. He started to arrange the elements in the periodic table, but based on another idea, which is the increase in atomic number. And you know that the atomic number is the number of protons inside the nucleus of the atom, and we consider it the idea of the element. So no 2 elements sharing or having the same atomic number. So by this way, or by this arrangement, all the elements fit with their positions, all the properties were periodic, and nothing they didn't have any problem. And now the periodic table fits with the description of the periodic law. The periodic law simply states that physical and chemical properties of elements are periodic functions to their atomic numbers. What does it mean? It means that from the atomic number, I easily determine physical and chemical properties of the element, or the atomic number has very good relation with the physical and chemical properties of the element. And when we go through section 5.2, you will understand more that I can determine these properties, or I can conclude these properties, or most of these properties, once I know the atomic number and the configuration of the element. And we will do this for elements in each group to show the pattern of the properties of elements in the periodic table. Okay? So the periodic law describes the periodicity of the elements inside the periodic table, which is the arrangement. What's meant by the periodic table? It is the arrangement of elements based on their properties. Okay? And they have, as we said, a very good relation to their atomic numbers. Okay? So we started with Mendeleev. He was the first one who arranged the elements based on their properties according to the increase of the atomic mass, which is the average weighted masses of the isotopes of an element, because some problems were found in Mendeleev's periodic table, that some elements didn't fit with their original place in this table, and their properties didn't match their groups. So Moseley started to build up the table based on another idea, which is the increase in the atomic number, which is the number of protons in the atom, and the periodic law states that the properties of elements generally are connected, or they are functions to the atomic numbers of these elements. It means we can determine these properties from the atomic number or relate the atomic number to the properties of these elements. Okay. Nowadays, or what we are using now, it's not Moseley's periodic table. Its name is the modern atomic table. Sorry, modern periodic table. The difference between the modern periodic table and Moseley's periodic table, both of them, of course, they work with the same idea, which is the increase of the atomic number of elements. But in the modern periodic table, we insert, or we added some groups to the previous one, or Moseley's periodic table, which are the noble gases, the group of noble gases, lanthanides and actinides. So by the discovery of noble gases, lanthanides and actinides, the periodic table was completed, and now it's known as the modern periodic table that is shown here. So this is the modern periodic table. As you see, it's made up of 18 vertical column, 1, 2, 3, 4, 5, up to 18, which are called the groups. And it has, it's made up of 7 periods, period 1, 2, 3, 4, 5, 6, and 7. The 2 rows down, the first row is called lanthanides, and the other one actinides. They are part of periods 6 and 7. Okay, each row in the periodic table is called period, and periods, they have a relation with the main levels of the atom, and we will relate the configuration to the periodic table in the coming section, inshallah. Okay. They found something called periodicity. What is the periodicity? When they compare the atomic numbers, focus with me here, of noble gases. Okay, they found a certain pattern or certain difference, fixed difference between the atomic numbers of elements in the same group. So when I subtract 10 minus 2, which is the atomic number of neon minus the atomic number of helium, it is 8. When I subtract 18 minus 10, it's 8. 36 minus 18, 18. Okay, 54 minus 18 is minus 36 is 18. And 86 minus 54 is 32. So they found that certain pattern or certain difference that is repeated with each group in the periodic table, especially group 1, group 2, group 1, group 2, group 13, 14, 15, 16, 17, and 18. And this difference is 8, 8, 18, 18, 32, which is called the periodicity. So I can, from this difference, determine the atomic number if the next element in the group. Yani if I asked you, for example, sodium, its atomic number is 11, found in period 3. What is the next element in its group? So now I'm talking about what? I'm talking about sodium. So when I add 8 to the 11, I can now predict the atomic number of the next element to sodium in each group. Also, I can use the idea of the buildup of the periodic table to determine the atomic number of the next element in his period or in its period. So the next element in the period, I will add 1. So it will be 12 and so on. Again, phosphorus, for example, its atomic number is 15. You can predict the atomic number of the previous element and the next element in its period. So the previous element in the period, I will minus 1, so it will be 14. In the next one in its period, I will add 1, so it will be 16. If I'm talking about the same what? The same period. If I'm talking about the same group, okay, I need to predict or to conclude the atomic number of the element above phosphorus in its group. So I will minus 8. Okay, so 18 minus 8, it will be 7. If I want to get the other one in its period, so I will add what? I will add 18. So 18 plus 15 is 33, and so on. Okay, so by this way I can use the periodicity to predict or to conclude the atomic numbers of elements in one group, and this successive arrangement of these differences 8, 8, 18, 18, 32, as we said. Okay, so by this way we're done, inshallah, completely with section 5.1. For question, or let's say for 5.2, in 5.2, we will relate the electronic configuration to the periodic table. First of all, I will put 3 different configurations for the 3 different cases of the configuration, and we will relate it now to the periodic table. In the configuration, we distribute the electrons over 4 different types of sublevels, which are the S, P, D, and F. Okay? The S can hold up to 2 electrons, the P can hold up to 6, the D can hold up to 10, and the F can hold up to 14. Okay? Now we will relate this to the periodic table now. All elements that are found in the S block, according to the configuration, we divide the periodic table into 4 blocks. The first block is called the S block, and the S block contains 2 groups, which are group 1 and group 2. And then we have the D block. The D block, the middle block of the periodic table, because the D can hold up to 10 electrons, so I have 10 groups in the D block, starting from group 3 up to group 12. When we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have the P block. The P block extends from group 13 up to group 18. And because the P sublevel can hold up to 6 electrons, so I have 6 columns or 6 groups in the P sublevel or in the B block. 1, 2, 3, 4, 5, 6. Down to the rows, the 2 rows down, which form the F block. The F can hold up to 14 electron, and the F block is made up of 14 column. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it means that I add 1 electron in each group, successive electrons from 1 to 14. The same for the S, because it can hold 2 electrons, so the S block is made up of 2 electrons. So again, when I divide the periodic table into areas, and these areas are called blocks, we have 4 different blocks according to the configuration from the 4 different sublevels. We have the S block, the B block, the D block, and the F block down. Each block is made up of certain number of groups that's equal to the number of electrons that saturate that sublevel, or the number of electrons that this sublevel holds. Okay? Now, so now we identified what? We identified the blocks. We need to identify now the groups. The groups are the vertical columns in the periodic table. Totally, they are 18, from extreme left to extreme right. And then we have to define the period. The period is the horizontal row. How many horizontal rows do we have? 7. From 1 down to 7, including lanthanides and the actinides, which make the F block. Now we will relate all of these information now to the periodic table. I'll start making the configuration. Let's start with sodium, for example, 11. Its configuration: 1s2, 2s2, 2b6, 3s1. Okay? And then I have let's say iron 26. Okay, so it's 1s2, 2s2, 2b6, 3s2, 3p6, 4s2, 3d6. Now 10, 20, 26. Okay, and let's take another one from the P block. Let's take silicon 14. So it's 1s2, 2s2, 2b6, 3s2. Now it's 12, 10, 12, 3p2. Okay? So now I have 10, 12, 14. Okay? So we did now the configuration of 3 different elements found in 3 different blocks. How can we determine the blocks? Okay. So when I get the block, I get the block mainly by the outermost sublevel. So my eyes are on the last letter that I wrote in my configuration. So back to the configuration and let's apply this. So the last sublevel or the outermost sublevel that I wrote is S, and here D, and down it's P. So when I ask you to determine the block, you will say simply this element is found in block S because the outermost configuration ends with the S sublevel, and this element, which is iron, it's found in block D because the outermost configuration ends with D sublevel, and this element simply is found in block P because the outermost configuration ends with the P sublevel. So now we are able to locate the element based on the block. Now I need to determine the period. So back to my rules. Okay, if I want to get the period, okay, how many periods do we have? 7. Why 7? Because the biggest atom is made up of 7 main energy levels. So to get the period, I will trace, or I will get the outermost main level. So my eyes on the highest coefficient, because the coefficient identifies the highest n, or the value of the main energy level, the outermost main level. Okay, so back to our configuration. If I asked you to determine the period in this case, so your eyes on the highest coefficient because it determines the highest n or the outermost main level. So this element is found in period 3. For iron, what is the highest coefficient? The highest number that you wrote is, yes, 4. So this element is found in period 4. Down to the silicon. So the highest coefficient or the highest or the outermost main level is the third. So this element is found in period 3. Okay, so now we're done with the location using the period and the group. Sorry, the period and the block. Now, how can we get the group number? The group. For the group, we need to apply different rules because it's different from block to another. Okay, if the outermost configuration ends with the S, like in sodium, so take the exponent of the S to be what? To be the group number of this element. So the outermost configuration, the outermost sublevel is S, take the exponent of the S. If the outermost configuration ends with P, okay, certain P, could be 3P, 4P, 5P, whatever, so take the NS, the same as before, because they both belong to the same main level, the same outer main level. Okay, so if the outer configuration is P, so you will add the exponent of the S plus the exponent of the P plus 10 in order to locate the group. Again, if the outermost configuration ends with P, so you have to consider the exponent of the S and the exponent of the P, okay, sharing the same N, the same main level, 3S, 3P, 2S, 2P, 4S, 4P. And then you add 10. Because if we go back to the periodic table, when you move from the S to the P, you are jumping above a gap of 10 groups, which make up the D block. So I have to consider them. Okay, so again, when we move from the S to the P, we move through 10 groups of the D. That's why we have to add 10 in order to locate the group in a proper way. Okay? The third option, if your outermost configuration ends with D, okay? So say, for example, 3D. Before the 3D, we have 4S. So we have to consider the exponents of both. So you have to add in order to locate it in a correct way for the group. So again, to locate the group, so we have 3 different options. The first one, if the outermost configuration ends with S, take the exponent of the S. If the outermost configuration ends with P, so you have to consider the previous S with the P and then add 10. If the outermost configuration ends with D, so you have to consider the exponent of the previous S plus the D. Okay? Let's apply this in our configuration. Now, we have sodium. Sodium ends with S, so I will take only its exponent to show the group. So this element is found in group 1. Iron. The outermost configuration ends with D. So I have to consider both exponents for the S and D. So this element is found in group 8. For silicon, it ends with P. So I have to consider the S and the P, and I have to add 10, so it will be 14. So this element is found in group 14. But I need to make sure that all of my location is correct. Back to my periodic table. You said that the sodium is found in S block, period 3, group 1. Let's check. S block, period 3, 1, 2, 3. Group 1, yes, it's found in group 1. Here is sodium, so I locate it correctly. Back to iron, block D, period 4, group 8. Block D, period 4, 1, 2, 3, 4, and group 8. Here is the 8, so iron is here. Period 4, group 8, within the D block. Okay. For silicon. Silicon is found in the P block, period 3, group 14. Okay, period 3, 1, 2, 3. I will move with period 3, group 14, down the intersection between both. So silicon is found here, and also it's within the P block. Okay, so now we are able to locate. The last thing in this part, if I asked you to determine the valence electrons, when I have to first define valence electrons, valence electrons are electrons on they are electrons on the outermost main level. And we said in the configuration what shows the outermost main level, we set the highest coefficient, if you remember. Okay? So it means that I will choose, in order to determine the valence electrons, I will choose the highest coefficient that identifies the outermost mean level, and then I will take its exponent or power to show the valence electrons there. So back to our configuration, and let's apply this concept on the valence electrons. Let's see. The highest coefficient is 3. This 3 has 1, so it means that the valence electrons here are 1. Okay? Again, how can we determine valence electrons? Valence electrons are the electrons on the outermost main level. In the configuration, the outermost main level is determined by the highest coefficient or the highest n, the principal quantum number, the highest n. And the number of electrons occupying the highest n is the valence electron. Okay, so because the exponent here is 1, so the number of valence electrons for sodium is 1. And determining valence electrons is very important for us because we will use it to determine the reactivity of this element later in this section. Let's apply the rule. The highest coefficient is 4. Okay, what is the exponent of 4? It's 2. So it means that the valence electrons of iron here are 2 electrons. Okay, again I choose what? I choose the highest coefficient. Okay, and then I take the exponent of this highest coefficient. The highest coefficient determines or identifies the highest period or the outermost main level. So here the highest coefficient is 3, but this 3 is repeated twice. So it means that I have to consider both exponents of the S and P. So the valence electrons here are 4. Why? Because the highest coefficient is represented by 2 sublevels, which are the 3s and the 3p. That's why I have to consider the electrons on both sublevels inside this main level, which is this third. So 2 plus 2 equal 4. So the valence electrons here are 4. So we're done now with identifying the blocks of the periodic table, the periods and the groups. Now we are done with the location and the naming of the 4 blocks of the periodic table. And now we are done with the relation of the configuration to the group number. The last objective of this section is determining the location and the properties of alkali metals, alkaline earth metals, transition halogens, and noble gases, which are different groups of the periodic table. Okay. Back to my periodic table. We will take groups in the periodic table in details a little bit and start to analyze the properties based on their atomic numbers. So we'll start with group 1, which are called alkali metals, then group 2, which are called alkaline earth metals, and then the transition elements, the outer transition that extend from group 3 up to group 12. And then we have mainly halogens, group 17 in nonmetals, and noble gases. And we will choose some elements from groups 13, 14, 15, and 16 that make up the metalloids. We will show their properties. And then the last thing, we will discuss the properties of the 2 rows down that make the F block, which are lanthanides and actinides. Okay, let's start with group 1. Okay, group 1, they start from period 2, lithium. Its atomic number is 3, sodium 11, potassium 19. Okay, and above group 1 we have hydrogen. Okay, so I write hydrogen here. I will not write it below the group 1, and I'll tell you why. Let's start with the configuration of lithium. Lithium 3, 1s2, 2s1. Sodium 1s2, 2s2, 2p6, 3s1. Potassium, let's use the noble gas notation. So I will use argon 18, 4s1. So what's common here in this configuration? When you focus, you will find that it ends with the same outermost sublevel, the same number of valence electrons, but different, of course, periods or different main levels. So I can say that the general formula, outer electronic configuration for group 1 all alkali metals is NS1. NS1 means the outermost sublevel is the S, and they carry only one valence electron. Okay, so we can mention their location. They are found in the S block, and they have one valence electron. And we have to mention the reactivity of these elements. These elements are the most reactive. And we need to know why. Why alkali metals are considered the most reactive metals. Focus with the configuration. For elements to be stable, they need to achieve stability. They need to have the same configuration, or their configuration matches the configuration of the nearest noble gas. So for lithium, for example, to be stable, it's so easy for lithium to lose this electron and become stable like helium. For sodium to be stable, it's easy to lose this electron and becomes stable like neon gas. For potassium to be stable, it's easy to lose this electron and becomes stable like argon, and so on. So we consider alkali metals the most reactive metals, as they are easily lose one valence electron in order to be stable. Okay, that's why they are considered the most reactive metals. What about their melting points and densities? Generally, they have low melting point and low density. That they are considered the lowest of all metals in melting point and density. Sodium, for example, the second element that we did its configuration here is soft metal. It can be cut with a knife, and it has very low density that it can float on water. Their appearance, they have metallic luster, and generally they are soft, less dense elements or metals. Okay? The story of hydrogen. Why hydrogen is not a member of group 1? Hydrogen, its configuration is 1s1, so it has the same outer configuration, which is ns1, as we wrote before. Why don't we consider hydrogen a member of group 1? So hydrogen doesn't belong to group 1 because its properties completely do not match the properties of group 1 or even the properties of any other group. That's why hydrogen is set apart in the periodic table, just placed above group 1 because its configuration matches the outer configuration of group 1, but it's not a member of group 1, or it's not a member of any other group in the periodic table because it has unique properties. Its properties do not match any other group in the periodic table. That's why it's set apart like this. And this is the first exception in location, or the first exception in the story of properties, that it's placed above group 1, but it's not a member of group 1 or a member of any other group. Okay? Now we're done with alkali metals. The last thing, that they are called alkali metals because they all react violently with water and form alkaline solutions. They are strong bases. That's why they are called alkali metals. Okay, they like to react with water and form lithium hydroxide, sodium hydroxide, potassium hydroxide, and all of these are strong bases. Back to the periodic table, and let's start group 2. Group 2 are called alkaline earth metals. Let's see the elements in group 2. We have beryllium, magnesium, calcium, strontium, barium, and radium. So we have many. Let's make the configuration of the first 3 and relate their configuration to their properties. Group 2, their name is alkaline earth metals. Okay, we have beryllium 4, magnesium 12, calcium 20. Let's make the configuration. 1s2, 2s2. Magnesium, let's use the noble gas notation. Neon 10, 3s2. Calcium, argon 18, 4s2. So what is common in their configuration? So the outermost configuration ends with NS2. NS2 means the outermost sublevel is the S, found in different periods, period 2, period 3, period 4, and they share the same number of valence electrons, which are 2. So they are found in the S block, and they have 2 valence electrons. What about their reactivity? What do you think? Yes, they are very reactive. Do you think more than group 2 or equal or less? Yes, it's less. So they are very reactive, but less than group 1 in their reactivities. So for group 2 to be stable, they easily lose 2 electrons. Beryllium becomes stable like what? Like helium. Magnesium loses these 2 electrons and becomes stable like neon. Calcium loses these 2 electrons and becomes stable like argon. Okay? But losing 2 electrons in group 2 is not as easy as group 1. So group 1 lose their electrons, their valence electron, much easier than losing 2 electrons in group 2. That's why group 1, they are the highest in reactivity, and then comes group 2 or alkaline earth metals. By the way, they are called alkaline earth metals because also they react with water to form alkaline solutions, and they are found mainly in Earth's crust. That's why they are called alkaline earth metals in rocks in the Earth's crust. Okay, now after the reactivity, we have their melting points and their densities. What do you think compared with group 1? So they are, or they have more or higher melting point, and they are more dense than group 1. Of course, because of their metallic bond. The metallic bond is stronger in group 2 than in group 1. And later, inshallah, in the coming quarter, when we take the metallic bond, you will understand more how do we relate the strength of the metallic bond to different metals. Okay, so we can say here that they have higher melting point and higher densities than group 1. And they are stronger than group 1, strong solids, and also they have metallic cluster. Okay. Do we have exceptions here? Yes, we have. Teacher, yes, helium. Its atomic number is 2. So when I make its configuration, it's 1s2. This outermost configuration, or this configuration, matches the same outer configuration of alkaline earth metals. Why didn't you put helium within the elements in group 2? So if I show you the periodic table, you will not find helium here. You will find helium there within group 18. And this is the other exception. Why helium is not a member of group 2? Okay. Although the configuration of helium matches the outer configuration of group 2, but it's unreactive element. That's why I cannot put it with group 2, because group 2 are very reactive. If you remember the reactivity, we said they are very reactive. So how come I join between very reactive elements with unreactive element or a stable element? So that's why they put it, or they prefer to put it with group 18, because all members of group 18 are noble gases that are completely unreactive. And this is the other exception. So the first exception was hydrogen. Its atomic number is 1, and its configuration fits with the outer configuration of group 1. It's placed above group 1, but it's not a member of group 1 or any other group. The second exception is helium. Its configuration matches the outer configuration of group 2, but it doesn't belong to group 2. It belongs to group 18, as it's completely unreactive or a noble gas. Okay. Now let's move to what's coming. So we're done with alkali metals group 1, alkaline earth metals group 2. Now let's take the transition elements, which is the middle block of the periodic table. So I will talk about the middle block or the transition elements. Typical metals. Okay, let's take the configuration of 2 of them. We have titanium 22, and we have copper, okay, 29. Let's make the configuration. Argon 18, 4s2, 3d2, right? 18 plus 2, 20 plus 2, 22. Okay. For copper, also I'll use argon 18, 4s1, 3d10. And remember, copper is one of the exceptions in the configuration. We take one electron from the s and the 4s and put it into the 3d in order to make the 3d completely filled with electrons. What is the other exception here? Also chromium. Its atomic number is 24. Argon 18, 4s1, 3d5. So chromium and copper, Cr and Cu, are the only 2 exceptions in the configuration. We take one electron from the 4s and put it into the 3d. For chromium, to make the 3d half filled, in copper to make the 3d full filled with electrons, and these two situations, for the d to be half filled or completely filled, is more stable. This situation is more stable for the atom. That's why the atom prefers to take this configuration or this distribution of electrons. Now, how can we determine the number of valence electrons if the outermost configuration is d? So we said, your eyes on the highest coefficient and take the exponent of the highest coefficient. So now can you tell me what are the valence electrons of transition elements? Yes, they could be, valence electrons could be 1 or 2, which are the exponents of the highest s, because it represents the highest outermost mean level, okay? And they are found in the D block. Okay, what about them? Reactivity. They are so reactive. They are reactive elements, okay? But the reactivity is a little bit less than group 1 and 2. So if I want to arrange the metals according to their reactivities, I will arrange them from the highest and move gradually less. So the highest of all is group 1, and then group 2, and then the transition elements. Even within the transition elements, we'll find variety of reactivities. Some of them are very active, like iron. Others are, they have weak reactivities, or they are low in reactivity, like gold. So we keep the jewelries made up of gold for several years, and they do not change or react. Also silver, also platinum. All of these are elements that have very low reactivity, and they are member of the transition elements. Zinc is reactive, iron is reactive, so we have variety of reactivities. That's why we do not have certain rule to apply in the reactivity here, due to the filled and half-filled D, okay, as a sublevel. Okay, their melting points and densities, they are, or they represent the highest of all. So the melting point of the transition elements and the densities of the transition elements is the highest of all metals. So also when we arrange them according to the melting point and density, it's the lowest in group 1, increases more in group 2, and it's the highest in the transition elements when we move from left to right in the periodic table across metals. Their appearance, they have great luster, or they are so shiny, but they have very important property that we use this property to define these elements, that they are perfect or good conductors. Okay, so transition elements are known as the good conductors for electricity and thermal energy. Most of cooking pots and pans are made up of different transition elements because they are good thermal conductors. And electric cords and wires, of course, the most common element, very famous to be used in making electrical cords and wires, is copper, a good conductor of electricity. So when I define some elements that are good conductors for electricity and thermal energy, so simply they are the transition elements. Now, back to our periodic table, and let's focus with the non-metals with group 17, and then we will discuss group 18. Group 17, they start with fluorine 9, chlorine 17, and then we have bromine 35 bromine. They are called what? They are called halogens. Let's make the configuration: 1s2, 2s2, 2p5, neon 10, 3s2, 3p5, argon 18, 4s2, 3d10, 4p5. How can we determine valence electrons? If the outermost configuration ends with N, S, N, P, so we have to consider both. 2s, 2p, so the valence electrons are 7, 3s, 3p, 7, 4s, 4p, 7. So they are found in the p block, and they have 7 valence electrons. And they are famous with their activity. They are described as the most reactive nonmetals. And we need to know why. Why they are considered the most reactive nonmetals. They need to be stable. How? They have 7 valence electrons, so they easily gain 1 electron, or even share 1 electron to be stable. So they gain 1 electron, and here gain 1 electron. So they can, or they are able to pay a lot of energy, to give off a lot of energy in order to gain this electron. So they catch it so easy to be stable. That's why they are considered the most reactive nonmetals. And they like very, very much to react with metals. So metals with halogens, they form a very common group of compounds that are called salts. And one of the most common salts that we always deal with is table salt or sodium chloride. So sodium chloride is made up of sodium metal and the chlorine as a non-metal, sodium from group 1 alkali metal and the chlorine group 17 halogen. So always they like to react with each other strongly to form a group of important compounds, which are the salts. And of course, salts are ionic compounds. Okay, now, when we focus with their appearance, we will find that they have variety of appearance, like especially their state at room temperature. Fluorine and chlorine are gases at room temperature. Bromine is the only liquid non-metal at room temperature. Okay, and the last one is iodine. So iodine is here. Here, iodine is solid at room temperature. So, respectively, according to their arrangement in their group, fluorine, chlorine are gases, bromine liquid, iodine, astatine are solids at room temperature. So by this way, we're done completely with group 17 or halogens. So they are found in the B block. They have 7 valence electrons. They easily gain 1 electron to be stable. That's why they are considered the most reactive nonmetals. They like to react with metals to form salts, and they have different states of matter with at the same room temperature. The first two, fluorine and the chlorine, are gases at room temperature. Bromine is the only liquid metal, and the iodine, astatine are solids at room temperature. Now, it's the time for group 18, which are the noble gases. And noble gases, I think all of you know their properties. Simply start with their configuration. Okay, we have helium, okay, 2, we said 1s2, and I will not use its configuration in order to locate, because we said it's an exception in location, okay? So I will start doing this from neon 10. I don't know why it works like this. Okay, neon 10. So neon, its atomic number is 10, 1s2, 2s2, 2p6. Argon 18. So I will use neon 10 to make the configuration of argon. So I start from 3, yes, 3s2 and 3p6. Okay, if I want to make krypton, 36. So I will use argon 18, 4s2, 3d10, 4p6. Okay, valence electrons, please. Okay, when the outermost configuration is p, so I will add s and p. So it's 8 here, 8 here, 8. Do you think that they need to be reactive? No. So when I write, they are found where? They are found in the B block. And they have 8 valence electrons. And they are unreactive. And we said the reason why they are unreactive, because they have complete outermost level. They achieve the octet structure, or having 8 valence electrons or 8 electrons on the outermost main level. What else? I said we will take some groups from, or some elements from the groups 13, 14, 15, and 16, which are the metalloids. The metalloids, they form a zigzag line. Let's make it with the green, okay? Here. Okay, so boron, silicon, germanium. Okay, silicon, germanium. We have the SPTE. All of these are transition elements here. Okay. Astatine also. So they are about 6, 1, 2, 3, 4, 5, 6 metalloids. They are found commonly in groups 13, 14, 15, and 16. Why we don't take the properties, common properties of these groups? As you see, these groups, they have or they contain different elements, metalloids, metals, and non-metals, so they do not share much common properties. So we will focus mainly on the properties of metalloids as common elements. So we have the metalloids. Metalloids are found mainly in the B block. And they are, or they have variety of reactivity. They do not have certain fixed reactivity. Okay, variety of reactivity. Okay, and they are all solids at room temperature. And the most common important property for them that they are called semiconductors. Semi means half. It's half a conductor. It means that at room temperature they are not so good in conductivity like metals and not so poor like non-metals. But at higher temperature they become very good conductors like metals. So this is the most important property for metalloids that are known. They are known as semiconductors. The last thing, and will be done completely with section 5.1 and 2, which are the two rows down, lanthanides and actinides. I will explain lanthanides and actinides here on the periodic table. Okay. Lanthanides is the first series, and they are called lanthanides because they follow the element lanthanum. Actinides are called actinides because they follow the element actinium in period 7. So for lanthanides, we start to fill the four. We fill the 4F sublevel, and in actinides we fill the 5F sublevel. They are found for lanthanides in period. They are part of period 6, and here they are part of period 7. And both belong to the F block. Each series is made up of 14 elements. The most important properties for lanthanides that they are shiny reactive metals. Shiny reactive metals, their reactivity is similar to group 2. So it means that I can use them or they react or they deal in reactions almost the same as the reactivity of group 2. And they are strong shiny metals. They are used mainly to make different types of steel. The most unique elements in the periodic table are actinides. They follow the element actinium, and they have one important common property, that they are radioactive. So radioactive, they are metals, but these metals are unstable. Their nuclei can radiate energy, different types or different forms of energy, that later, inshallah, in the 4th quarter, we will take a whole chapter about the radioactivity, and you'll understand more and more about actinides. By this way, we're done with the explanation of 5.1, 5.2. Good luck in the exam, inshallah.